Okay, this is 8.3, Evaluating Logarithms. Our goal is to evaluate logarithmic expressions and approximate the logarithm of a number to any base. Ramon, can you read? Jackson?
Sure. Jackson Jackson knows that a rumor spreads very quickly. He tells 3 people a rumor, but at the end of the next hour, each of these people has told 3 more people. Each person who hears the rumor tells 3 more people in the next hour. Jackson has written an algebraic model n equals nt, n at t equals 3 t plus 1 to represent the number of people who hear the rumor within a particular hour, where n at t is the number of people told during hour t, and t equals 1 corresponds to the hour during which the first 3 people heard the rumor and start telling others.
Okay, so the question is, in which hour will an additional 2,187 people hear the rumor? So here's our number of people, that's what n represents, and t is our hours after the rumor starts spreading. So we're looking for an n value here of 2187. So we can very quickly set up this equation, nt is equal to 2187, sub that value into the formula that was given at the beginning. So we have 2187 is equal to 3 to the exponent of t plus 1. So without knowing anything about logarithms, one thing we can do, one strategy, is to make the bases the same, and then we can relate the exponents. Okay, and this is what we were taught in grade 10 and grade 11 when we had to solve for a variable that was in an exponent. We made the bases the same, we solved, then we could correlate or equal the exponents. So that's what we do here. So 3 to the exponent of a value
Pardon me, Mr. Mason, please contact the office, Mr. Mason.
is equal to t plus 1. So that exponent now we need to make the total value 2187. So they do that by guess and check. So 3 to the exponent of 5 is 243, to the exponent of 6 is 729. Finally, they figure out that 3 to the exponent of 7 is 2187. So we can replace this value of 2187 with 3 to the exponent of 7. Okay? Once we do that, we can eliminate the bases because they're the same, and we can equate the exponents. So 7 is equal to t plus 1. Any questions about that and how we ended up solving for t equals 6? That's not a bad method for...
Pardon me, Mr. Mason, please contact the office, Mr. Mason.
It's not a bad method when we have a relatively simple question like this. Okay, it didn't take very long to get up to 7, but we can get values that are much greater, so we need to figure out another way. One other way is to use a graphing calculator. So we would just graph this function, okay, where n is on our y-axis and t is on our x-axis, and we get this function occurring down here. And then we set the y value, or n value in this case, to 2187, which will just be a horizontal line like this. And we find out where they intersect. Okay? And that will give us the value of t once we trace that back down here. Okay? That again is not that convenient for us because it's involving a graphing calculator, which we don't all have. So we're going to find the final solution, which is the one I prefer. There's no guess and test. We actually use algebra. Okay? So the way we do that is we use logarithms. So we're going to rewrite the exponential in logarithmic form. Okay, so here's our, again, the number of people that have heard the rumor. We sub that into the equation, so we're left with this equation. What we really want to find out is the value of t. And remember how we defined logarithms. This whole value here, this value here, is the exponent that 3 needs to be raised to get 2187. Okay? So just if we look the equation previously, the exponent that 3 needs to be raised to get 2187 is t plus 1. Okay? So we can then equate log 3 2187 to t plus 1. I'm going to say that one more time because this is probably the trickiest part maybe. This value here is the exponent that the 3, the base, needs to be raised to equal 2187. Okay? Based on this equation, we know if 3 is raised to this exponent of t plus 1, we get 2187. Therefore, the exponent that 3 needs to be raised to get 2187 is t plus 1. Okay? Any questions? All right, so once we have this, we can then isolate for the value of t. So we move the 1 over, and we can just use our calculator and we can solve for t. Okay? So again, we get t is equal to 6. Okay, we're going to see a bunch of examples in this lesson of that. All right, let's go straight to them. Example 2. Use reasoning to evaluate the logarithmic expression. So use the definition of a logarithm to determine the value of each expression. So log 4 64 equals x. Determine the exponent. So remember, logarithms mean this value is equal to the exponent that 4 needs to be raised to get 64. So we can rewrite this equation then. 4 needs to be raised to the unknown exponent, x, to get 64. Any questions how I went from this formula to this formula? Because that's important. It's by definition of what a logarithm function is, right? So the base to an unknown exponent gives me the value of 64. Okay? Once we have this, again, we're finding the same base. Okay, so we're rewriting 64 in terms of the base of 4, and then we can solve for x. Okay? So here, same idea. The base 3 has to be raised to the unknown exponent x to equal 1 over 27. We need to take this number now and convert it to the same base. So it ends up being 3 to the exponent of negative 3, because this is 1 over 3 cubed, which is 3 to the negative 3. Okay, yeah?
Why didn't you just solve it with the calculator?
Because we need to understand how logarithms work. Okay, because there's going to be variables in here later on that we won't just be able to plug into our calculator. If you don't understand this concept, then you're going to get lost really quickly. Okay? But you're right, yeah. If you had this log 3 base on your calculator, you could just punch this in and get x. Right. But this is the process of understanding how logarithms work. Okay? Yeah.
So how would you get 1 over 27 to 3 to the exponent of negative 3?
Okay, so it's right here. So 1 over 27 is 3 to the exponent of 3, right? So when you have an exponent on the denominator, it becomes negative, right? Okay? All right, so then we get x is equal to negative 3. Any questions on that one? C. So same process. 2 to the exponent of x gives me negative 4. 2 to the exponent of x is negative 4. In this case, there's no exponent, there's no value of x that we cannot square and get a negative number. So we cannot put any value here for x to get negative 4. It's just not possible. Okay? Therefore, there's no solution. Okay? What does that mean on the graph? That means the solution is down here, negative 4, right? So when is this function negative 4? Well, it's never. It never touches it. Okay, so that's why. So there's the representation of no solution on the graph, and there's the algebraic reason. You cannot raise 2 to the exponent. Yeah.
How come when you bring the 4 over, it's still negative on the other side of the equal sign?
Here?
Yeah.
Because you're not bringing it over. You're redefining this equation based on what the definition of a logarithm is. Okay? You're not moving the 4 over like you would traditionally, what you're thinking, right? By reverse operations. You're not doing that in this case. You're saying that negative 4 is the value that 2 needs to be, this whole thing is the value that 2 needs to be raised to the exponent of x to get this value. Okay? So it's not like you're doing reverse operations and moving equations around that are attached to logarithms. You're redefining this equation to equal this. And how and why? It's based on the definition of a logarithm. So this value is equal to the exponent that 2 needs to be raised to give you 4. Okay? So what does 2 need to be raised to? It needs to be raised to the exponent of x to give you -4. So it's not kind of the traditional sense where you're moving variables across equal signs. All right, next one. So this takes us back to grade 11 where we have a cube root, okay, which is the same thing as, raised to a third, okay. So here now we have the base of 5, so it's going to be 5 raised to the x is going to be equal to the cube root of 25. Now we can rewrite the cube root of 25 as the cube root of 5 squared, and now we can combine the square and the cube root to 2/3. Any questions about that? That's a review from last year. You guys all remember that? So a cube root of 25 is equal to 25 raised to the exponent of 1/3. Okay, 25 is the same as 5 squared, all raised to 1/3, and then exponents you multiply, so you get 5 to the 2/3. Okay. What's your question?
5 to the x.
Sorry?
How did you get 5 to the exponent of x?
5 to the
No, like on the left side.
here? Yeah, this is what we've been doing this whole time, right? Note, we've been taking the base and raising it to the unknown exponent is equal to that. Oh, it's okay. Yeah, there's a base of 5. Okay. All right. Determine the approximate value of log 547. So there's a couple ways to do this. One way, again, is if we use graphing technology, we can just graph this equation now. Okay. Once we do that, we can see the value of x when y is 47. So we draw the line y equals 47, the horizontal line, and then we find the point where they intersect, and we trace that down, and we get our x value, which is here. Okay? Again, not the preferred method because we're not all using graphing calculators. So there's another couple methods. One is to use guess and check. This is pretty straightforward. It's a pretty simple alternative. So we know 5 squared is 25. We know 5 cubed is 125. So we know if we're trying to get 47, it's in between 2 and 3. And we know it's closer to 2. Okay, so we start testing values. 2.5, too high. 2.25, too low. We keep testing. We end up finding 2.39375 gives us very close to the value. Okay? No. So you could use logarithms to do it, right? In this case, in this section, we haven't learned exactly how to solve this. In the next 8.4, we're going to see another way to solve it, okay? But for now, for this section, if you get a question like this, you can do guess and test. And this doesn't take that long, right? We're just halving each time.
Yeah.
So we go 2.5, sorry, we go 0.5, 0.25, 1.25 we added, so we're just halving. So it didn't take that long. Example 4. So use the log key on your calculator to evaluate the following logarithms. Explain how the calculator determines the values. So one reason why we just don't want to use our calculator is because we might get a question like this that asks us to explain how does it determine the values. So what did anybody remember what I said 2 days ago about when there's no number here? Yeah, it's 10. The default is 10, right? Default is equal to 10. So what the value of log 10 is then, it's saying what exponent does 10 have to be raised to? So this value is the exponent that 10 has to be raised to give me 10. Okay? So in this case then, x is equal to 1. Okay? The next one here, what exponent does 10 have to be raised to give me 100? So x is 2. Okay? Finally, what exponent does 10 have to be raised to give me 500? That's down here, C. So 10 to the raised to the x is equal to 500. X is equal to 2.7. And this again is guess and check for now. Okay? All right, number 5. Examine some general properties of logarithms. Evaluate each of the following logarithms. So log 6 to the exponent of 1, we know by definition that that means 6 raised to the exponent of x is equal to 1. And x, this whole value is equal to 0, so x is going to be equal to 0 here. Okay? So the value of the expression is the exponent to which 6 must be raised to get 1. A power equals 1 only when its exponent is 0. To verify, let the expression equal x and rewrite the expression in exponential form. We're fine there. Okay. So log 5. So base 5. So this is what value? This is the value that 5 needs to be raised to get 5 to the exponent of x. Okay? So in other words, 5 to the exponent of an unknown, y, is equal to 5 to the exponent of x. So the reason why we use y is because x was an unknown already. So we're not going to say use x. So that's why we used y here. Because it's the unknown exponent that it needs to be raised to get x. So in this case, y is equal to x. So log of 5 to the base 5, exponent x is equal to x. Okay? Next one, 6 raised to the exponent of log 6x. So we can rewrite that as log 6y is equal to log 6x. Okay? And then we can solve dividing both sides of log 6 out, we get y is equal to x. So log 6 log to the base 6 x is equal to x. And that subs back in for the left side to equal the right side. Any questions about that? Okay.
Sure.
Yeah.
Just leave it at y equals x.
Sorry?
You just leave it as y equals x. You have to put 6 to the log 6x equals x. And just say y equals x.
Yeah. This is just a verification step. To verify, let the expression equal y and rewrite the expression in exponential form. So yeah, you could just end up with y equals x. Yes. That's the solution, yeah. Okay. Key idea. So simple exponential equations can be solved using a variety of strategies, expressing both sides as powers with a common base and then equating the exponents. So this is when we find the common base. That's what we did at the beginning. And then we equate the exponents. So the exponents are equal. Graphing, using a graphing technology, and then set the point of intersection. So we graph, we set our y value, and then find the point of intersection. You can solve for x. Okay, and rewriting an equation in logarithmic form and simplifying. This is the big one, right? This is the one we'll be using for the most part. A logarithm is an exponent. The logarithm of a number to a given base is the exponent to which the base must be raised to get the number. So this is by definition from the last 2 sections we looked at, right? And we use this a lot in this section. Logarithms of negative numbers do not exist because a negative number cannot be written as a power of a positive base. Okay, so this is important. You can't ever have log equal a negative number. Okay? And that goes, goes by the definition. You can see that on the graph as well. A logarithm written with any base can be estimated with a calculator using graphing technology or guess and check. The expression log x is called a common logarithm. It means log 10x, and it can be evaluated using the log key on a calculator. Okay, so the following are some properties of logarithms where a is greater than 0 and a is not equal to 1. So log a1 is equal to 0. So this is the value that a needs to be raised to get 1. Any value raised to the exponent of 0 is equal to 1. Okay, so this a value could be any base. Log AAX is equal to x. So again, going by definition, this whole value, or the value of x, is equal to the exponent that a needs to be raised to give you a to x. So what exponent do I have to raise a to give me a to the exponent of x? It's going to be x, of course, right? So if you have the same base logarithm as the value here, then you can eliminate this and the solution would just be x. A to the exponent of log a, so now we have a base to an exponent of a logarithmic with the base a, is also equal to x. Okay? Any questions on any of those properties?
Just repeat the last two.
The last two? Okay.
Yeah.
Okay. So this, by definition, is saying this value, this whole value here, which is x, is the value that of the exponent that a needs to be raised to give me ax. So what value does a need to be raised to give me ax? X, yeah. So, or they use y, right? So the value that a needs to be raised to is x. Okay? Sorry, a log okay, we'll look for this one. We'll look with some numbers again to try and simplify it a bit. This expression is written in exponential form. Let the expression equal y and rewrite in logarithmic form. So this is written in exponential form. We want to rewrite it as a logarithm. So we're going to let this whole expression equal y. Okay? Once we let that expression equal y, we're going to take the base log 6 of y. So we're taking the log 6 of both sides. So we have once we take the base of both sides, we can see that y is going to be equal to x. So therefore, looking at the general term, when a is raised to a logarithm with the same base a, where the number being raised is x, this whole term is equal to x as well. Okay? That's because this is equal to the value that a needs to be raised to get log ax. Alright? Make a little bit more sense once you guys get some practice. Any other questions?